Hi, this is Dr. Liu, and in this video I will introduce to you what is kinetic energy. So kinetic energy is energy associated with motion, kinetic motion. So something's moving, it would carry kinetic energy. So let's see how this energy is written. So I'll use E sub K. And sometimes textbooks will just opt with a capital K for simplicity. So both versions work, and because of its associated with an object moving, we are going to include the mass and also include the velocity, except that the velocity is squared and the result is multiplied with 1/2. So it's not exactly obvious at this moment, right? Why there a 1/2 and why there a square on the velocity, not on the mass? But I assure you that later this will become more obvious why the energy has this kind of strangeness. Okay, so since this is a new concept, let's take a look at the unit, right? So the unit of EK so we have here is mass, right? Here's mass unit, and the velocity's unit is length over time, and we square that. Okay, so the most common unit is just to use kilogram for mass and meter for length, and then a second for time. So I can define this new unit called J, or joule. So I can put the rest in parentheses, and that is one. I have kilogram, then I have meter squared, and per second squared. So second to the -2 power. So these are all multiplied together. Okay, so it's a bit complicated, right? But we can rewrite it in 1 kilogram meter per second squared. We're missing a meter, so this whole thing is multiplied by a meter. And this whole thing, kilogram meter per second squared, well, meter per second squared, this is the unit of acceleration, right? This is unit of mass, this is unit of acceleration. Mass times acceleration, according to Newton's second law, is force. So this is unit of force. This is a Newton, right? 1 Newton. So if you summarize, the unit is 1 Newton meter. Although this is not the most fundamental units such as the kilogram, meters, and second, we're only using these 3 units in the entire kinematics and dynamics in this semester, because this is all we need. So this is the most fundamental way, but this is easier to remember. A Newton times a meter, and it also has its implication, which is how you would transfer energy. There's a way to transfer energy is by applying a force and sustaining the force over a displacement of some distance. So I will introduce to that in the next video, but let's just leave it here. A Newton times a meter, so that is what a joule is. So we'll just remember joule for now. That describes energy. Okay, so now we know the kinetic energy's expression. Let's calculate a few objects, a few typical things, how fast they are and how much energy they have. So let's calculate this one here. This is a kinetic energy of a projectile. So remember, back in the projectile motion lab, we fired projectiles, little plastic, yellow plastic balls. So they have velocities close to about 5 meters per second, about 4.8. So let's say projectiles. So we have mass. We don't really know the exact mass of these plastic balls. We never thought about measuring them, right? Because that wasn't necessary back then. So I'll give it an estimate. Let me think about that. I've used them a lot, but I never really measured their masses. But I think they're less than 50 grams because I've used 50-gram hangers. They're heavier. So being plastic, let's say 25 grams. So it's an estimate. So that is 0.025 kilograms. If I divide this 25 by 1,000 to get kilograms, and the speed, and let's also have an estimate of 5 meters per second. So this is just something small that gets launched at a moderate to high speed. You can toss something quite easily at that speed. Just pick up a pebble and just toss it. So how much kinetic energy does an object like this have? So kinetic energy, let's calculate 1/2 mv squared. This is 0.5 times 0.025 times 5 squared. So let's use our calculator. 0.025, 5 squared. Okay, so we have a fraction of a joule, 0.3125. Let's just keep 3 digits after decimal. That's 312 if I round to even. So it's only a fraction of a joule. If you just pick up an everyday object, a pencil, maybe a keychain, and toss it, it's got that order of magnitude of energy, joule, fraction of a joule, maybe a few joules if you toss it really hard. So let's go ahead and find out another EK of a person. So a person, let's give this person 75 kilograms of mass. And how fast can a person move? So if I walk, say if I walk at 2 meters per second, this is actually relatively fast. So I'm kind of in a hurry, but I'm not running. There's kind of a discontinuity between how fast you can walk and how fast you can run. There's like you can't really walk very fast or run very slowly. You go from kind of a fast walk to a slow running. So this is kind of a fast walk, 2 meters per second. So if you're looking down at floor tiles, these are 1 foot by 1 foot floor tiles. This bigger tiles that you might find at St. Cloud State. So basically 3 tiles will be close to 1 meter. So you have to basically dash through 6 tiles per second. So it's kind of I'm moving in a hurry, I'm not running yet, I'm a bit late for class, right? So that's how fast it is. I'm just giving you an idea. The situation is someone is just trying to get into a classroom and they're late. So let's calculate the kinetic energy. So a person in a hurry, walking fast, 1/2 mv squared. So 0.5 times 75 kilograms, that's just an average build person, maybe with a backpack, and 2 squared. So let's bring up our calculator. 0.5 times 75 times 2 squares of 4. So we have 150 joules. So 150 joules. So now we're talking about hundreds of joules, maybe in the order of 100 joules. That is for a human being. Maybe walking slow will be less, walking fast is more. Jogging, running will start to go into the several hundred joules of energy. So that's for just a person. So let's calculate one last thing, a vehicle. Okay, so for a vehicle, let's assume that the vehicle has 1,200 kilograms of mass, and it is moving at some highway speed. So let's try to make up a number. So 55 miles per hour, and if you convert that into meters per second by dividing by roughly 2.2, so that's let's see, that will be 50 over 225, close enough. So let's assume about 30 meters per second. So it's a little more than 55 miles per hour. Let's take a look at what that is. So, 30 times 2.2. So roughly 66 miles per hour. So you're just driving on a highway, driving your car. Maybe there's a passenger in the car, including the driver. So that's the total mass. And how much kinetic energy does this system have? This exercise basically, we just repeat the expression 1/2 mv squared. We want to memorize that, and then also we want to know how large a joule is. Everybody knows how long a foot is. You can just look at your own foot, and it's in that order of magnitude. And how long a meter is. If you have a meter stick, you get a pretty good idea. And then this joule is a new thing. So we're trying to establish this idea, how fast something is moving and how much energy it probably has. So let's keep going. 1,200 times 30 squared. Because we're squaring velocity, and this time we have a higher velocity. Squaring that will give us quite a large number, 900, right? 30 squared. So we have a very large number, 1,200 times 30 squared, that's 900. So this is in the hundreds of thousands, 540,000 joules. So if I keep 3 digits, 5.40 times 10 to the fifth, so 540,000 joules. So this gives you an idea that a car moving at highway speed will have about 500,000 joules, hundreds of thousands of joules. And if you're just driving a car on a local road, the speed is about half that, and then your kinetic energy is about a quarter of that, because the square of the speed, if you're half the 30 and then you're quarter of the 30 squared, so you'll still have roughly 100,000 joules. So this gives you an idea of energy. This is fraction of a joule or a joule. A small object, you toss it. And a person moving, this is 100 joules. And a car moving, 100,000 joules. Right, nice orders of magnitude. Yeah, there's motions in anywhere in between is, or even less than that. Maybe a small insect moving, or even more than that, much bigger, such as the moon orbiting the Earth, or Earth orbiting the Sun. Anything bigger. So these are the things we're experiencing every day. So now we have an idea about the order of magnitude of such thing. So this is kinetic energy, and you may ask, okay, this kinetic energy, where does it come from, right? It comes from the fact that we have mass. Okay, yes, it also comes from the fact that we have velocity, but velocity is relative, right? Say if you're in a car, this car here, the car has 540,000 joules of kinetic energy. That is only when the car is observed by someone on the ground who claims that this car is moving at this speed, right? So if you're on the car and you use your own reference frame, that means you consider yourself at rest. So you will observe the car yourself and your passenger all at rest. So you have no kinetic energy. On the other hand, everything else is moving towards you or away from you. They have velocities, they have masses, they have kinetic energy, right? So it's kind of confusing. So what I want you to think about this is relative to the observer. Frame of reference. So basically, if you change this frame of reference, say if you go from someone on the ground observing your vehicle to someone, say, on your vehicle or on a different vehicle moving at a different velocity, then the kinetic energy value is going to change. So we call this thing is not invariant from changing of observers. So we need to be careful when we're saying velocities and speeds. Speeds would basically velocity without direction. We want to make sure that all these quantities are coming from the same exact observer, and that observer doesn't switch role to another observer until at least the question is done, the calculation is over, such as some energy conservation process that involves the kinetic energy. So this is something of kind of a caution. Do not change reference when you're doing energy, because kinetic energy depends on that reference. So it's not, let's say, it's not invariant to the reference frame changes. Thank you.